Hi everybody, welcome back. So today I'd like to talk to you about hypothesis tests, specifically about one-sided hypothesis tests. Now, this is similar to what we've been doing before. Here's the big difference. Before, when we were doing very simple two-sided tests, these guys right here, our null hypothesis was that the average was a particular number. And what that gave rise to was, very naturally, two-sided tests. So if our hypothesis was that this population mean was actually this particular number, then it could be wrong if we were very much greater than that number or very much less than that number. And you would reject this hypothesis if you were either very high or very low. So that was a two-tailed test. The natural thing when your null hypothesis is that you're equal to something and the alternative is that you're not equal to. In this set of slides, we're going to talk about inequality hypotheses. So now what we're going to do is look at research hypotheses that say that the average is bigger than a particular number. Like maybe we claim that there's more than 2 scoops of raisins in Raisin Bran. Or that, one symptom of a particular disease is that your body temperature is bigger than 98.6 degrees. Something like that. In which case, the logical complement of that, your null, would be, not that it's bigger than, would be the opposite of that. So it would be less than or equal to. And then we could also have less than alternatives. For example, the number of days that you would have to be treated by one drug might be less than a particular number. And then the logical complement of that would be that it would be greater than a particular number. So these inequality hypotheses come up all the time in life and in research. And it's good that we practice doing them. I'll say that I think the hardest part about inequality hypotheses is sorting out what your null and your alternative is and figuring out how to translate that to a critical value. But pretty much all the other steps are the same. But enough talking. Let's start looking at more specifics. And just to reiterate, we're still following the same usual steps of a hypothesis test. Everything is the same except what you see in red there. We just want to be very careful once we start doing inequality hypotheses, just to be very clear on what our null and our research hypotheses are. And then when we translate that to acceptance and rejection regions. As I said, everything else is going to be the same. So let's think about what do we mean by a null and an alternative hypothesis. And I'll keep switching between alternative and research hypothesis. The thing is, these two things, alternative or other known as research hypothesis, that's what you secretly want to prove. This is why you have a criminal trial, for example. You have the trial because you secretly believe that the person on trial is guilty. Now you have to stack the deck against yourself and prove that this is true, that the person is guilty. And you do that by presuming that the person is innocent. Okay, so you show up at trial, the person is presumed innocent. You got to put a whole bunch of, the prosecutor has to have overwhelming evidence that the person is actually not innocent, the person is guilty, and then you've proven what you want to prove. So just try to keep in mind this first particular thing, that the research hypothesis is what you actually want to prove. I think if you keep that in mind, everything else will be a whole lot simpler. So here's an example. Do smokers have lighter babies? We know that smoking causes a whole bunch of different adverse health effects. Could one of those also be lower birth weights for babies? So notice that the expected effect here, it's only in one direction. We're not saying that smokers have different weight babies than non-smokers. We actually claim that they have lighter babies, that smoking has an adverse effect, not just that it has a different effect. Okay, so our research hypothesis then is that the average weight for smokers, I'm just going to call that mu for average and S for smokers, the average weight for smokers is less than the usual 7 pounds. The null hypothesis is then the opposite of that. So if mu of S is less than 7, the opposite is mu sub S is greater than or equal to 7. It's traditional, by the way, to always include this equal sign in the null hypothesis. That's just traditional. It turns out if you have a continuous distribution, the probability of exactly 7 is always 0. So whether you include that in your null or your research has no practical effect. I'm just telling you that in practice, the convention is always include the equal sign in your null hypothesis. That way everyone's on the same page. That's a minor point. So let's suppose we want to run this test. We're going to conduct it at the 5% level. And let's presume, just for the sake of this example, that we know that the population standard deviation, sigma, is equal to 1. Now, I'm making an implicit assumption here. I'm presuming that the spread, the distribution of all possible birth weights is the same regardless of whether you're a smoker or not. So it's not like we have a standard deviation for smoker babies and a standard deviation for non-smokers babies. I'm just going to presume they're the same thing just to keep the math simple. We'll complicate that in further videos down the line. So for now, let's just say that the population standard deviation of birth weights is equal to 1 no matter whether you're a smoker or not. Now let's translate this into critical values. So we know the population standard deviation. So this bell-shaped curve that I'm drawing is going to be drawn from a z distribution. And then our question is, how do we come up with critical values? You see, before we had our distribution and we had symmetrical critical values. We would reject if we were in either tail. But that's no longer the case. Now we have an inequality as our null hypothesis. So we need to adjust from a two-tailed test to a one-tailed test like you see here. Now, we're going to presume that the defendant is innocent. We're basically presuming that smoking doesn't have an effect. In which case, we would accept the null. In other words, not reject the null. But let's keep our terminology simple. Accept the null. Our null hypothesis in this acceptance region. And we would only reject this null hypothesis that average birth weight is less than 7 only if birth weights were significantly less than 7. And so what we need to do then is figure out, what do we mean by significantly less than? What is this particular value of z that gives us the appropriate rejection region? Now we know we're testing at the 5% level, so we need 5% in here, and we need 95% in the unshaded area, that right-hand side. Okay, so let's find the value of z that gives us a left tail probability of 5%. So find the value, some value, such that the probability is not 95, this is 0.05. Right? We want 5% to the left. So we can just look at our normal z tables, or we can use Excel like we normally do. There'll be a link up there somewhere up on top. There's my finger. Right. Can you see that? There. Right there. There's going to be a link on how to calculate z values if you need a refresher for inverse calculations. But let's just bring up Excel and do it real quick. Okay, so we start with an equal sign. We need an inverse calculation from a standard normal. So inverse from a standard normal. And then we give it the probability. We want 0.05. And what we get is negative 164. We can get rid of some of those decimals. And that's what we have right here. This particular value is negative 1.64. All right, so if we get a test statistic that's bigger than negative 164, we're in the acceptance region. If we get a test statistic in this blue area, a test statistic less than negative 164, then we would reject. So the only thing that we have left to do is calculate our sample, collect our sample, calculate our sample statistics, our test statistic, and see what region it's in. So let's say that you went out and you did a quick trial. You looked at the birth weights for 49 babies from moms who smoked. You calculated their average weight was 6.95 pounds. A little bit less than 7. But, of course, if there was no difference and smoker moms had 7-pound babies, they were not all exactly 7. Some are going to be greater and some are going to be less. So what we really want to know is the weight sufficiently less to get rid of our null hypothesis? Is 695 as an average from 49 babies sufficiently less than 7? Well, the only way to answer that question is to calculate the test statistic. The formula should be familiar. Take our sample average, subtract off the hypothesized mean, and divide by the standard error. The standard error is, as usual, the standard deviation of x divided by the square root of the sample size. So our sample average was 695. We hypothesized that the population average was 7. And this is where it's useful, by the way, that we had this right here, where the null included the equals. Because that's what this says here. We're subtracting off the mean from the null hypothesis. Okay, so 695 minus the hypothesized mean divided by the standard error. Plug in a 1 for your standard deviation. That was given to us. We said our sample size was 49, so square root of 49 is 7. And so we just plug that into a calculator and we get negative 0.35. Now our test statistic was negative 1.6, our critical value was negative 164. Our test statistic was negative 0.35. Our test stat fell somewhere here. So we're in the acceptance region. We're not in the rejection region. We cannot reject the null. This H sub 0. So in other words, we've got to accept the null. And that was the zero hypothesis, that smoking doesn't cause lower birth weights. In other words, we just don't have enough evidence from these 49 babies to make that claim yet. This is all made up evidence, by the way, made up numbers. I'm not thinking that smoking probably has some effect. We're just playing around with numbers as an example. Okay. The thing I want you to notice, though, is even though our sample had lower birth weights, it wasn't sufficiently negative to put us in the rejection region. So we couldn't reject the null hypothesis. All right. So we basically have to accept the null and probably just say that the mean is the same for smokers versus non-smokers. Right? This part right there, the equal sign. Maybe we can work out another one. So in this case, we're going to do a greater than research hypothesis. This is also made up, but it's something that's in the news right now. That's why I'm filming from the guest bedroom. So let's say that you make a drug and you think it's going to prolong the lives of coronavirus patients, the ones who are like seriously sick and have been intubated. Basically, they're on ventilators. They have a tube down their throat pumping air into their lungs. And so these are the ones these folks you're really worried about, and you think maybe this drug is going to help prolong their lives. So let's just suppose, and I'm making up these numbers, but it's something that's on my mind lately. Let's say that the average intubated patient lives for 20 days past intubation. Now, we'd like to think that our drug prolongs life. So our research hypothesis, in other words, the alternative, also called H sub A, is that the average lifespan for an intubated patient with our drug treatment is bigger than 20 days. The logical complement of that will be the null hypothesis. And that's got to be that mu is less than or equal to 20. In other words, we can't presume that our drug says what we say it, our drug does what we say it does. We got to prove that. So we're actually going to presume the opposite of what we want to actually prove. Right? So we're presuming this, and we're going to presume that when we construct our confidence interval. So we run a pilot study of 64 patients. We see they lived for 21 days. All right, that's good. That's good because that's consistent with what we want. But there's tons of variation. Can we actually claim that our drug works? Is this enough statistical evidence for us to overturn the presumption of innocence and overturn the null hypothesis? Well, we need a little bit more information to find out. So let's dig deeper. So the other piece of information that we need is we need to know what level we're testing at, what significance level. That's up to us as researchers, but we should do that before we collect our sample. Let's say now we're testing at the 1% level. And the other piece of info that we needed is what the population standard deviation was. Now, if we don't have the population standard deviation, then we're just going to use the sample. And then when we're constructing our critical values, rather than drawing from a standard normal, we would draw from a t distribution with n-1 degrees of freedom. But that's a minor complication, and that thing comes up all the time. If you got to estimate sigma with s, use a t. So if s, t. But let's brush that aside. Let's say somehow we knew that the population standard deviation was 4 days. Now we have all the information we need for our test statistic and our critical value. Okay, so let's do the critical value. Now we're doing a one-tailed test. So we're not doing rejection regions on both sides. We need to have a rejection region on one side or the other. Which side? I think this is the part that's confusing for students. The thing to keep in mind is that we're going to presume the null hypothesis is true. And we're only going to overturn the null if we get enough evidence against this. All right, so here's what the distribution of days living on intubation is. We think it's centered around 20. And if the null hypothesis is true, and that if we give these people the drug, it's less than or equal to 20, then we would only reject that if we had something much bigger than 20. So our rejection region would be here on the right. And that's what this picture here shows. We have a rejection region here, and we've got our acceptance region to the left. And the reason we can do that is we're presuming that mu is less than 20. So we're presuming things on the left-hand tail. We would only reject that if we were way to the right. Now our level of the test is 0.01%, so our rejection region is also a 0.01, 1% probability in the right tail. That means 99% is in the unshaded area. So what's our critical value? Well, it's going to be this particular value of z that gives us a left tail, a less than probability, equal to 99%. Now we can just key this into Excel. Key in equals norm.s.inverse 0.99, and it'll spit out 2.33. Notice a number that's bigger than 0. All right, so our critical value here, this guy, is 2.33. Next thing we got to do is actually collect our sample, calculate our test statistic, and see whether we're in the rejection region or the acceptance region. So let's pull up our sample info. Okay, so what's our test statistic? Now, we ran our test of 64 people. We gave them our drug, and they lived 21 days rather than 20 days. So among our treated patients, they live on average 1 day more than the usual. We need to translate that into standard errors. That's sigma divided by the square root of n. And we said a couple slides ago that the standard deviation there was 4. So we just plug in 4 for sigma, 64 for the sample size. Key this into a calculator, and we get a nice round number of 2. So where does that put us? Is that acceptance region or rejection region? Well, we're somewhere here. For our test statistic, we're not in the rejection region. We're in the acceptance region. What are we accepting? We're accepting the null. We don't have enough evidence to overturn the null. Even though our patients lived longer, it's not a convincing statistical result. And so we would not be able to conclude here either that the drug is effective. The only ethical thing you can do is collect more data and rerun a test, maybe more than 64 people. Anyway, that's it. That's how you do less than or greater than research hypotheses. Let's just summarize what we've seen. We have one-sided hypothesis tests. We could have alternative, that's our research hypothesis, and our null. If your alternative or your research hypothesis says that the average is less than a particular number, then it better be significantly less than. If our research hypothesis was that the average was bigger than a particular number, then we're in this case here, what we really want is our test statistic to be much bigger than this particular number. Now this is usually done in terms of the null, so let me just backtrack a little bit. We secretly think that the average is less than a particular number. Let's presume that it isn't. All right, so if it isn't, then we would presume bigger than. Dumb luck would have us be maybe a little bit less than. But all of that would be consistent with the null. And it's only if we got a test statistic that's way less than what we were expecting that we would reject the null and instead go with the alternative. I find that to be a little bit convoluted. So the simple version is, if you think that mu is less than a, some number a, whatever that is, draw a sample, calculate a test statistic. Let's hope that it is way less than a. And if it is, yay. Right? That's the hypothesis that we go with. So I think this summary slide here is kind of useful. It kind of lays out the two options, a less than alternative and a greater than alternative. The other thing is that the critical values come up a whole lot. -128, -164, -233 on this side, or for doing greater than alternatives, and these are just positive numbers. These critical value numbers come up all the time, over and over again, and so not a bad idea to memorize them. It's also kind of inevitable that if you do enough practice problems, you'll start remembering them. But this is a quick cheat sheet for you to work from. There's some things that we should keep in mind. Usually, you're comparing your test, the dosage from the effect of the drug on a placebo, and so really you should be comparing the average from your drug versus the average from a placebo. I compared it to the overall population of non-drugged people. Really, what we should be doing is comparing samples, some that got the drug, some that got the placebo. So, we probably have to estimate the standard deviations of the drug population and the placebo population. That also implies that we're going to be using t-tests. And then the crucial thing, though, is that we're also comparing not just an average to a particular number. We're comparing one kind of average, a random variable, to another random variable. And that brings up a whole different set of complications. In fact, we're going to have a completely different video on hypothesis tests comparing two samples. We will do that next time. As I said, we'll get to all of those complications next time. In the meantime, thank you for listening and take care. Bye-bye.